Kia ora guys. Today we're going to look at pages 34 and 35 of WalkerMaths, and the idea that we're looking at is rates of change. So in front of me here, or in front of us, we've got an orange, and for the sake of today's lesson we're going to pretend that this orange is a sphere. So we're going to look at two measurements of our orange. We're going to look at its volume, and we're going to call its volume obviously V, and volume is measured in centimeters cubed. We're also going to have a look at its radius, and we're going to call radius R, and radius is, as you know, measured in centimeters if the volume is measured in centimeters cubed. So let's make a couple of assumptions. I reckon that this orange, for the sake of an easier lesson, has about a radius of, let's say, 2 centimeters. Let's pretend that this is a 2 centimeter radius orange. And then its volume, if its radius was 2 centimeters, we would have to put that into the volume of a sphere formula. And so that would be V equals 4 over 3 pi r cubed. So if I wanted to know the volume of this orange, which I think might have a radius of about 2 centimeters, which is totally not true, by the way, it's probably closer to 3 centimeters, I would have to put it into this formula. But actually on the screen right now, I've got that formula mapped out. So here I've got that formula put into Desmos. On the x-axis is the radius, so 1 centimeter, 2 centimeters, 3 centimeters. And on the y-axis, we've got the volume. So that would be 10 centimeters cubed, 20 centimeters cubed, whatever. So let's say if it was 2 centimeters in radius, then the volume would be, oh, tell me, where are you? The volume would be 32 pi over 3, and we'll work out what exactly that means in a bit. All right, so what we're going to do is, instead of just looking at a radius input and a volume output, I want us to think about how fast this orange would be growing in volume if we knew at what point of radius. I'll say that again. We're going to think about, if the radius was 2 centimeters and it was sitting on the tree, how fast would this orange be growing if it was a perfect sphere? Right? So to do that, we are going to need to find a derivative. So the derivative here is, our only variable is R, and we're looking at the change in volume. So we're going to have to type in, or write, change in volume over the change in radius. So this looks tough because there's a fraction and this like scary looking pi, but actually 4 over 3 pi is just a number. So we're only actually dealing with the r. So what power is the r to? It's to the power of 3. So we just multiply this number by 3, and it's really handy because multiplying this by 3 just gets rid of that over 3 there. So it's going to be 4 pi, and then all we need to do is reduce the power by 1, so 3 minus 1 is 2. So the derivative of the volume of a sphere is 4 pi r squared. If we want to find out how fast is actually I'm going to show you a picture of that. So this blue dotted line is the derivative going up here. That's how fast the volume of the orange is growing in relation to the size of its radius. So let's have a look at our orange. How fast is the volume of this orange growing as its radius, or when its radius is 2 centimeters? So what we have to do is we just substitute a 2 into r there. So that's going to be 4 pi 2 squared. 2 squared is 4, 4 times 4 is 16, so that makes it 16 pi. Or, to be honest, in calculus you can get away with writing 16 pi, but just to get an understanding, we're going to do a little bit of calculation so we can sort of see what that number is. So we're going to go 16 times, where's times? There. Pi equals. So that is 50.27 centimeters. Oh, actually, what is the unit there? Because we're looking at how fast the volume of the orange is growing. Now, volume is measured in centimeters cubed, but we're trying to find out how fast the volume is growing in regard to the radius, which is centimeters. So let's write a sentence here. So the volume of the orange is increasing, because that number is positive. So we're going to write increasing. If it was a negative, you would put decreasing. Is increasing by, I'm going to write about because I'm feeling lazy right now, by about 50 centimeters cubed per centimeter of radius. Or what am I missing? Per centimeter of radius when the radius is 2 centimeters. Now, obviously, when you write your answers, they're not going to have to be as long-winded as mine. I just want you guys to get an understanding of like exactly what's going on. Right, so now, here's the other thing I want to have a look at. Let's work out, like, because I feel like 50 centimeters cubed is a really fast growth rate if the volume at the time is only actually somewhere around about, what did we decide? 34 centimeters cubed. So how is it growing that fast? It seems ridiculous. So what we're going to do is I've got a little gradient function here. So this triangle shows you how fast the orange is growing at each point, right? Because it's the gradient at each point. So let's pull this up to 2 centimeters where we're focused on. And you can see that along the base here, this is a radius growth of 1 centimeter, right? Between 1.5 and 2.5. And you can see that the growth in volume is exactly, it's from about, what is that number? Like 8.2-ish up to about 58.2-ish. So you can see that the volume grows 50 centimeters cubed when the radius grows by 1 centimeter. So that just shows you that that growth rate is actually the case. Right, fact of the matter is, yeah, spheres grow really fast. The bigger the radius is, your sphere gets like more and larger as your radius gets larger. It's like a triple factor because it's cubed, right? Yeah, the only thing that gets different at page 35 is that they will sometimes give you the volume and you will need to go to the original formula and work out what the radius would be at that volume. Then you do these steps. But rates of change, all you really have to do is find out your input variable, then differentiate it, then substitute in that input variable, get an answer. So I got the answer 50.27, and then you need to put it in context with correct units. Honestly, a lot of the time you're going to be better off drawing a picture. So with this one, you might want to draw yourself a sphere and have a picture of what exactly you're looking at. So I'm looking at how fast the radius is increasing, and I'm seeing how big the volume becomes as the radius increases. So drawing like a picture is really helpful, especially for working out what your variables are. Anyways, I hope that helps, and that's all.